Hi guys, we're talking about derivatives of inverse functions today. First, I'm going to define for you or remind you of what it means for a function to be one-to-one. A function is one-to-one if every input has one output and every output has one input. So a couple of things to know about one-to-one functions. They pass both the vertical line test as well as the horizontal line test. And their inverses are also going to be one-to-one. Here's an example. So if I just look at f of x equals x squared, it wouldn't pass the horizontal line test. But when I just keep one branch of it, keeping the entire range, let's say this branch where x is greater or equal to 0, it's one-to-one, and so is its inverse, as you can see, root x. In general, right, you can see that one-to-one functions are either always going to be increasing or always decreasing. And that's a really important idea, and that's where the calculus comes in. So fancy words for that are strictly increasing, you would say monotonically increasing, or strictly decreasing, monotonically decreasing. So my question for you is, how can you use calculus to show that a function is one-to-one? Pause and answer. Okay. Well, hopefully you know that when you check the derivative, right, if you get that the derivative is positive, then it means that the function is increasing and monotonically increasing if it's always positive. Or if the derivative is negative, monotonically decreasing, meaning that it's always going down. So that would also be a way to show that the function was one-to-one. Prove that f is one-to-one. Pause the video. Okay, so you check the derivative, and you can see that it's always positive, right? 3x squared is always positive. You're adding 1, still positive. So f is monotonically increasing, therefore f is one-to-one. That means every input for f is got one output. Every output has one input, and you'll see why that's important. Okay, so another question here. Here's f again. Find the inverse value at x equals -1. But do that without finding the inverse function. Pause the video. You don't need to find f inverse. What you need to realize is that if AB is on the graph of f, then BA is on the graph of the inverse. So if I'm asking you to find f inverse of -1, let's say that it's equal to A, it means that f of A would equal -1, and you have to figure out what input gives you an output of -1 for f. So you're solving this equation. A cubed plus A minus 1 is -1, and then you get this equation, which by inspection, you can just see, guess and check, right, that A is equal to 0. And because f is one-to-one, there's only one answer to this. There's only one value of A where the output is 0. So that's equal to 0. So you could factor to see that too. So that's the answer. F inverse of -1 then is equal to A, which is equal to 0. Okay, so now let's get into the calculus. So the relationship between the derivatives of inverse functions at their inflection points. So I'm giving you here the graph of f of x equals x squared. Again, just the part where x is greater or equal to 0, keeping it one-to-one. The derivative is 2x. Notice that the derivative at x equals 2 gives me 4. So the slope of the tangent line here at x equals 2 is equal to 4. Now we're going to look at the slope of the tangent line on the inverse of this at x equals 4 at the image point. So here is f inverse. It's root x. Here's the derivative of f inverse, which is 1 over 2 root x. And the derivative at x equals 4, and this is how you write that for the inverse at x equals 4, is 1 over 2 times root 4, or 1/4. So, I mean, the fact that you're taking the derivative at 4 and you're getting 1/4, there's no relationship there. That's just coincidence. What I want you to notice is that for these two functions at their image points, 2, 4, 4, 2, their slopes are reciprocals of each other. And we're going to use that idea to answer more complicated questions now. So big idea. Here's a function. Here's its inverse, reflections over y equals x. And the derivative of f at x equals a is the reciprocal of the derivative of g at x equals b, right, at the range of a. Or the derivative of g, if I flip this around, at b is equal to 1 over the derivative of f at a. And I'm writing it this way because this is often what you're trying to find. You won't know what the function's inverse is, so you won't know g, so you won't be able to find g prime b directly, but you'll be able to find f prime a, and you'll be able to take the reciprocal of it to get this answer. Let's try that with an example now. So let's say that f of x is equal to x minus 2 squared plus 6, where x is greater than 2. So past the vertex, this is now 1 to 1. You can show that. And I'm asking the derivative of the inverse at x equals 15. And I want to do it without finding f inverse x. Pause the video and try it. So you'll notice, right, I'm saying find the derivative of f inverse at x equals 15 means there's some output a where a15 is on the graph of f. This is how I always start. And if I find a, I can find f prime a, flip my answer over, and that's going to be the derivative of f inverse at x equals 15. So I figure out the a value. Right? I see, oh, there's two a values when I solve algebraically, but only one of them is keeping f1 to 1. Remember, a has to be greater than 2 because x is greater than 2. So the answer for a equals 5 is correct. Okay. So now I find the derivative of f at a, so the derivative of f at 5. There's the derivative of f. Here's the derivative of f at 5. And I take the reciprocal. 1 over f prime 5 is 1/6. So that's the answer for the derivative of the inverse at x equals 15. Let's try one more example. This one's from the packet, number 4. You try it first, pause the video, and then you can watch my solution. F and g are inverses. You're finding g prime 2 if f is equal to this function. First of all, I'm showing you that f prime is always positive, f is increasing, and therefore 1 to 1. I know that I'm looking for the derivative of the inverse function at 2. So I find the output there by setting the output for f to be 2. I'm solving this equation by inspection again. This is a cubic. So you can see that if a is equal to 1, I'm going to get a solution. You could use the rational roots test to also see that a is equal to 1 if you remember that. And there's only one answer, right? That's the point. You don't have to look for more solutions because f is 1 to 1. So you know that a equals 1 is the only answer to this as long because f is monotonically increasing. So therefore, I find the derivative of f, 3x squared plus 2. I plug in the value, a equals 1. I get 5. And now I've got the relationship that g prime 2 is 1 over f prime 1. So that's 1/5. And that's the answer.